finally, now I can say that we are reaching the top of the course. Basically, I know that's how I compare reaching the point where I start introducing Maxwell's equations, sort of finalizing Maxwell's equations. I compare it with reaching the top of the mountain. That's why I put this picture up here, right? Because it's basically, yeah, the most important point where you can finally present the whole and complete foundation of the course of electromagnetism, right? Okay, and you remember which equations I claimed that they're going to be in the set of Maxwell's equations. Gauss's law, right? Then Amperes law and Faraday's law. So far we introduced 3 equations. So of course at some point we will introduce the 4th equation, but that will be very fast, right? But first, let's revisit Amperes law, right? Oh, slides forward. Okay, let's revisit Amperes law, and you will understand why. And now it's time for me to confess again, to tell you that, yeah, bless me, Father, for I have sinned. I actually didn't tell the whole truth at some point about some important thing. But from the educational point of view, it's nice to present material in layers, right? Then it's easier to digest, to understand, right? So, but anyway, let's revisit Amperes law to see, do we have any troubles up there, right? Okay, so here's Amperes law. You remember we used it a lot. So where we have integral over a closed loop, right? B dot ds equals to mu naught times I enclosed. And you remember, first thing before you start applying this Amperes law, we usually picked a closed loop, which we called an Amperian loop, right? Closed loop, which we called an Amperian loop. Then, yeah, of course, then we usually start evaluating this integral, and then next we usually started looking at enclosed current. And what did I tell you about the procedure of finding the enclosed current? Not much. I usually told you something like this. So we have an Amperian loop, closed loop, right? And just look for any currents which are physically enclosed or embraced by our Amperian loop, right? So that's what I told you. And you know what? From the mathematical point of view, from the point of view of mathematics, it sounds so lousy. Oh my God, yeah, from the mathematical point of view, which is trying to be very, very strict, precise, right? So this process of finding enclosed current is really lousy, right? So, but again, from educational point of view, at that point it was fine. And now we need to present the correct procedure that we have to follow in order to find the enclosed currents, right? So now let me outline the correct procedure. So once you picked an Amperian loop, right? Okay, basically it's the first step, pick an Amperian loop. Then the second step, you need to pick any surface enclosed by your Amperian loop. What does it mean, surface enclosed by the Amperian loop? Pretty much it means that that surface must end on this Amperian loop all the time. So it can be, for example, flat surface, right? But of course it ends on the Amperian loop. Or some kind of concave surface, like kind of baggy type surface. Or maybe on this side, baggy type, or towards that, in that direction. Or maybe you can come up with very, very complicated surface. But again, the key word, it must end on the Amperian loop. So that's what it means, enclosed surface. So pretty much after we pick an Amperian loop, the second step, you need to pick any surface enclosed by the Amperian loop. And the key word, any, right? So then once you pick that surface, then you have what? You have current, right? And you have surface. Current is basically like an infinitely long line, right? Of course, you can talk about point of intersection. So if that wire, this current intersects your surface, your chosen surface, then that current is an enclosed current. So that's the correct procedure. Again, first we pick an Amperean loop, then that enclosed surface, and then if your current physically crosses your surface, then that current is an enclosed current, right? So 3 steps. And I want to emphasize on that word any surface. You should be able to pick any surface enclosed by the Amperean loop. It pretty much means that you can pick any surface, right? As I said, maybe simple, flat, or maybe some kind of baggy type. And it doesn't matter which surface you pick, everyone should be able to end up with exactly the same enclosed current. We're not discriminating, okay, physics in this case, are not discriminating people on in this way, right? So basically we can say we follow that Civil Rights Act of 1964, where, according to which we're not supposed to discriminate people based on what, no, race, gender, color, religion, I don't know, height, weight, and now we can add an additional category based on their surface to find the correct enclosed current. Anyone, it doesn't matter which surface you pick enclosed by the Amperean loop, everyone should be able to get exactly the same current, enclosed current, right? Okay, so now after giving this correct description of the process of finding enclosed current, now let's apply that, and let's apply in the examples which we used so far, Right? You remember where we used that? Okay, that's basically description. And now examples where we used Ampere's law successfully. So for example, a straight wire, you remember. So first of all, of course, we usually pick an Amperean loop centered on the wire, right? So we can use the symmetry, and then, of course, according to this procedure, the next step we should pick a surface. And let's say I give you a chance first to pick your surface. Usually students like simplicity, right? As simple as possible, right? So let's say you pick the flat surface. Again, enclosed by the Amperean loop. So let's say you pick this pinky surface. You see, flat. And you see, again, it is enclosed by the Amperean loop. So let's say that's your surface, S1, right? So which current is enclosed? Obviously, this current I crosses this surface at that point, so this current I is our enclosed surface, right? Okay, so you're getting this value, or this current, enclosed current. Now let's say I don't like simplicity, I like to overcomplicate things. So let's say I will pick this baggy type surface. Yeah, overcomplicating. And so in my case, so what I'm getting in terms of the enclosed current, the same. You see, exactly the same current I crosses my surface. So, and in this case, I'm also getting exactly the same enclosed current. It will be equal to I. So you see, in both cases, we're getting exactly the same enclosed current. So no troubles. Everything seems to be working, right? And that's why we use this Ampere's law in examples like that, right? And you know what? Now, you remember my speculations about geniuses, troublemakers, right? Who basically usually come and ruin our sand castles. So you remember back then Faraday did something like that, right? With this Faraday's law. And here now it's time for a brilliant theoretician, Maxwell. He was really, really great in theoretical physics, right? So he came, right? I think by that time he described some rings around the planet, right? I remember, and he got some award even, and probably at that time he was bored, so he came to this field, right, and started playing with electromagnetism, right? So what he did, he looked at this and he said, you know what, it's too boring, it's too simple, this example. Let's make things more complicated. And he suggested, let's insert a capacitor in the middle of this wire. Why not? We claim that this Ampere's law is a fundamental law. It means that you should be able to apply it anywhere you want. No restrictions. So he said, let me insert a capacitor and see what we are going to get. So let's follow his steps. So he took a capacitor, right, in the process of charging. So positive electrode, negative electrode, right? So of course there will be electric field between plates, uniform, right? So, and let's say current is flowing into this capacitor, so charging this capacitor. And of course current is over there, right? And so he said, let's apply our Amperes law. So of course, we picked exactly the same Amperean loop centered on the wire. And so now let's find enclosed current using different surfaces. So of course, students as usually would go with the simplest one, the flat one, again enclosed by the Amperean loop, right? So, and of course, what will be the, so it's a surface S1, right? Flat one. And of course, if you apply Amperes law, where is it here? So the right-hand side we're not going to calculate. Of course, it will be just integral of b dot ds. And what's the value of enclosed current for this if you use surface S1? Our current I, because this current I physically crosses your chosen surface, flat surface S1. So in this case, of course, we can write Amperes law in this way. So it will be integral of b dot ds equals mu naught I. Then Faraday said, or not Faraday, Maxwell, sorry, Maxwell. It's too simple. He probably was the guy who liked to overcomplicate things a lot, right? Overthink things. He liked to overthink things a lot, right? So he said, you know what? Since I have a right to pick any surface I want, let me choose the surface like this, which goes through the gap of the capacitor. And again, it is enclosed by the Amperean loop. So pretty much again, even that surface, it still ends on the Amperean loop, right? And then it goes sort of very, very baggy type. It goes through the gap of the capacitor, right? Okay, so he picked the surface, and according to the rule, he's supposed to get exactly the same current. But if you use that surface S2, you see I label it as S2. So what are you going to get as an enclosed current? Nothing, because this current I, it goes through the hole, right, in the loop, because here there is no surface, right? Surface is over here. So it goes through this hole, reaches the positively charged plate, right? And again, our surface just goes around that plate. So pretty much there is no current. There is no current crossing this surface S2. Physically, right? You see, there is no current physically crossing that surface S2, this orangey surface. So if you apply Amperes law, right, in exactly the same way, so what is I enclosed? Of course, the left-hand side is exactly the same, because in both cases, the same Amperean loop is used. So, but now I enclosed is 0. And of course, now what we're getting, that integral over the closed loop b dot ds equals to 0. Oops. So in this situation, we have that integral equals to mu naught times I. In this case, we have that the same integral equals to 0. So you see, left-hand side is exactly the same, but the right-hand side is different. Of course, it's impossible, right? In both cases, we're supposed to get exactly the same result. It means what? It means that something is fishy. It means that this law is not complete, because he just demonstrated an example where Faraday's, not Faraday's, damn it. Probably I like the name Faraday, so it keeps jumping out of my mouth, right? So it means that Amperes law is not a true law right now, because he found an example where Amperes law failed to work, right? And so it means that it must be somehow adjusted, fixed, right? And it's not uncommon. It happens in physics quite often, right? So before physicists settle down in terms of fundamental equations. So if somebody finds some new phenomena which cannot be explained, so they spend some time adjusting laws, fixing them, right, in order to explain that phenomena, right? So Maxwell found one example, and and of course, actually, which part of the law, which side of the law failed to work? Obviously the right hand side, because on the left hand side we have this integral b dot ds, right? So there's nothing wrong, it's exactly the same for both surfaces, right? But obviously the right hand side, the current side, is with the problems. And again, nothing wrong with the universal constant mu naught, right? So that's just a constant. Obviously some kind of current is missing in our law. So it looks like we need to add maybe some additional current in order to make it work. So that was Maxwell's speculations, right? So he found this problem, and since he realized immediately that something is wrong on the current side, so he decided, you know what, let's try to construct somehow a new expression for the current, hoping for the best. Basically, what he did, it's not a derivation, it's more like a, I'm going to present it in a second, right? It's more like a fudging, right? And again, it's not unusual in the world of science, right? So they see there's something, right, where there's a problem, and they try to come up with some term, some construction in order to add to the equation to explain it, right? So they will construct and see, does it explain it? Not completely close, but not completely. So they will start massaging it more, trying to fix it, and they will do it until that additional term or additional factor will be able to explain what they observe. All right. It's not uncommon, so it's quite often. It happens quite often. So pretty much something like this Maxwell did. So let's try to follow his steps. So since it failed to work with the capacitor, of course, he started dancing around a capacitor, right? So again, current entering the capacitor, right? Positive electrode, negative electrode, plus Q, minus Q, spacing D, right? Electric field, uniform electric field, just a regular story about the capacitor. And so he started thinking, so he needed to get a new term with units of current, right? Somehow. And so he started speculating. So what if I, right? What if I get some expression for the charge, right? In terms of what is over here in the picture. And then, of course, he needed to get a new quantity, new term, which would have a units of current. So how can you get units of current from the charge? You need to differentiate it with respect to time, right? In order to get units of current. That's how we introduced current. You remember dq over dt. So if he he thought if he manages to get q in terms of something, then he would try to differentiate that with respect to time, and he would end up with some term which has unit of current, and he decided to try that. So let's follow his steps. How can you get current in the presence of the charge in the presence of the capacitor? So you can get it from the definition of capacitance. Definition of capacitance. C equals Q over delta V. So of course, charge will be equal to C times the potential difference across this capacitor. So C times delta V. Okay, of course, at some point he will try to differentiate it. But you know what? What are we trying to fix? We're trying to fix the fundamental law, adjusted, right? And of course, it must be written in terms of fundamental quantities like electric field, magnetic field, currents, and so on, charges, right? But right now we have capacitance. Capacitance, very useful, very practical thing, quantity, but it's not something fundamental. No. It must be removed from here. Then potential difference. Again, it's a ridiculously practical quantity. Everyone uses it, but again, it's not a fundamental quantity. You remember, like in the Faraday's law, we tried to dump that EMF and write it in terms of electric field. What was the reason? Because it's not a fundamental. So let's rewrite C in terms of something and delta V in terms of something. Again, dancing around our capacitor. So C, you remember, since it's a parallel plate capacitor, we can use the formula which we derived for a capacitance of parallel plate capacitor. Epsilon naught A divided by D. Okay, let's try to use it. Then delta V, potential difference across a parallel plate capacitor. We also remember the expression. somewhere closer to the beginning of the semester, we introduced it. It's a E times D. Delta V, potential difference across the plates of a capacitor, equals to electric field times the spacing between the plates. Okay, so let's plug them instead of C and delta V, and you see what happens to D spacing. D will be cancelled, right? Okay, good, encouraging when stuff gets cancelled. And as a result, we're getting epsilon naught electric field times area. Guys, what is electric field times area? What is this? Can you recognize which quantity is that? Electric field times area. This is the electric flux. Electric flux, look, it's a number, basically number of electric field lines crossing the surface A, right? Of course, yeah, if you take area vector in the same direction as the direction of the electric field, right? So it's a flux, our old friend, which we introduced, I don't know, a few weeks ago. Electric flux. So we can write that charge equals to epsilon naught times electric flux. Wow, it looks so interesting, so encouraging that we can get something new, ridiculously new, completely new. All right. Okay, so he got this for the charge, and then of course he wanted to get some term which has units of current. And I explained to you, so now we just need to differentiate this charge with respect to time in order to get units of current, right? So I equals dq over dt, right? And also, okay, all right, and he differentiated that with respect to time. D over dt, epsilon naught times phi. Of course, epsilon naught is a universal constant, So of course, we can take it outside of the sign of differentiation. So we're getting epsilon naught times a rate of change of the electric flux. Okay, this is completely new construction. No one has ever seen this construction before, right, in the equation. So he got this, and so he decided to give it a cool name. It's very important. After getting something new, you need to give it a very interesting name, cool name. The name is displacement current. A displacement current. Don't think, and of course don't tell anyone that I told you that don't think about the meaning of this term, displacement current. Pretty much because there is no meaning. Back then, 100 or 150 years ago, when this was a hot subject in physics, they had some ideas what might happen inside of this capacitor, right? So of course they tried to model, they tried to create some mechanisms, and according to those mechanisms, they thought that this is some kind of displacement current, right? So probably back then this term had some meaning, but then all those ideas, those mechanisms turned out to be complete rubbish, right? So that was all trashed, but the name survived. Maybe because it just sounds cool, displacement current, right? But again, don't think about the meaning. So it's just a nice name for this construction. Displacement current, I sub d equals epsilon naught times rate of change of the electric flux. So that's what he decided to add to the right-hand side of the Amperes law, hoping for the best. And actually it worked. But before we adjust Amperes law and start discussing, I want to emphasize on one thing. Look at this big line. So on this side we have dq over dt. Here, dq over dt, it's actually also equal to the actual current flowing into the capacitor. dq over dt equals to I, actual current flowing into the capacitor. So on this side we have the actual current. On this side, on the right hand side, we have this newly introduced, who knows what, displacement current. So it means what? Numerically, actual real current charging the capacitor in this case equals to this newly introduced displacement current, numerically only. It doesn't mean that their natures are the same. just numerically, it means that if this current is charging the capacitor is 5 amps, then this whatever displacement current is also has the units, or it has a value of 5 amps. It's sort of like, if it's still confusing, look, this comparison. Let's say we have one elephant, big elephant, and its mass is 5 tons, right? So an elephant, its mass is 5 tons. And let's say here we have tons of, let's say, lots of mice, and their total mass is also 5 tons. So masses are the same. One elephant, 5 tons, tons of mice, also 5 tons, right? So numerically, they're equal, but it doesn't mean that their nature is the same. Elephant and mice, they have nothing in common, right? Except that the fact that they are living creatures, right? But masses are the same. So here the same. We have numerically this current equals to that current, but only numerically. They have nothing in common in terms of their nature. Nature of this actual current, it's actually drift of electrons, that current which we introduced a few weeks ago. But in a few, okay, let me probably jump ahead. What is the nature of this current? Is just basically, okay, I don't want to say, right? I will say in a second, right? But anyway, so this displacement current, so he introduced and he decided to add it to the right-hand side of the Amperes law. And since he found the problem with this Amperes law and he fixed it, properly, right? So it started working. Of course, as a result, of course, his name was added to the name of this law. So now it's no longer just an Amperes law, it's the Ampere-Maxwell's law. If you in the future find another example where this law fails to work, then your name will be added. I don't know, Ampere Maxwell, no, Smith law. It's like when I was in undergraduate school in Ukraine, we had one professor. He used to teach us quantum theory of solid state physics, right? And he was sort of like a star in the solid state physics. And there was one equation, all right, which consisted of, or consists of 4 names. First name hyphen, second name hyphen, third name, and then the name of that professor was, right. So if you manage to find a new example where it fails to work, and if you fix it, then of course your name will be added to the end of this train of names, right? But so far only 2 names, Ampere, Maxwell's law. So you see he added a displacement current to the right-hand side of the equation. So we have I in, this is I in, it's the actual current flowing to the system. This I displacement, it's this construction. Okay, so now let's look carefully at this new current, displacement current. Let's look at the properties of this displacement current. Exactly the same picture, I just copied and paste, right? And so again, I just copied and paste the this expression which we used to define the displacement current. So first of all, what can you say about the displacement current, for example, here, outside of that capacitor? Of course, it's 0, because electric field is not 0 only between the plates of the capacitor. You remember properties of a parallel plate capacitor? Electric field is not 0 only between the plates. Outside, it's 0. So since we have here electric flux, rate of change of the electric flux, and if the electric field is 0, of course, flux will be 0. So displacement current outside of the capacitor is 0. So displacement current is not 0 only between the plates. So first, we need to remember that, right? Then second, numerically, I just emphasize on that properly, right? So numerically, this actual current equals to the displacement current. So now we can introduce this sort of like an arrow direction of this displacement current, sort of in the same direction as the actual current, and numerically these two currents are the same, and of course over there also, right? So here we have that actual current, and here we have displacement current between the plates, and numerically it's the same value, 5, for example, 5 amps, 5 amps, and then again 5 amps. So you see, now we have sort of like a true conservation of current. You remember when we introduced conservation of current without a junction point, I told you, right? So if there is no junction point, that current must be exactly the same at any point, right? At any cross-sectional area. But if you had a capacitor back then, so before the capacitor, you have, let's say, 5 amps, then there is a zero current, and then again 5 amps. So you see, back then, without displacement current, we kind of didn't have a true conservation of current, because if you have a gap, then their current is zero. But now, once we introduce this displacement current, we have sort of like a true conservation of current. 5 amps will be everywhere, right? So this fact, and then the last one, that this displacement current has nothing to do with a flow of charge. A real current, this real current over here, yeah, it's a charges drifts, electrons drifts, giving us this current. This displacement current has nothing in common with that. We only call it a current, displacement current, we only call it a current because it can produce, or it produces, not can, it produces magnetic field like if it was a real current. So here we have a current, actual current I, and of course it produces magnetic field around itself, right? Like we discussed already many times. Now we introduce this kind of displacement current, which has nothing to do with the drift of charges, and we call it we call it a current only because it also produces magnetic field like this actual current. So around this displacement current, which is between the plates, will be also magnetic field produced by this displacement current. And actually, now at this point, probably you should start realizing, so what is actually behind this fact that this displacement current produces magnetic field. So look carefully at this structure. It's a rate of change of the magnetic flux. If area, for example, the same, because flux is E times A. If area is the same, right, you can take it outside and you will get epsilon naught times A, and then what? dE over dt, rate of change of the electric field. Basically, it means that changing in time electric field produces magnetic field. That's the nature of this displacement current, and the fact that it can produce magnetic field. Because over here, between the plates, we have electric field. And that electric field changes in time because capacitor is in the process of charging. Changing in time electric field produces magnetic field. It's sort of like yesterday, in the previous class, I think, or the class before, when we discussed Faraday's law. In the Faraday's law, changing in time, magnetic field produced electric field. And now, reverse is correct. Changing in time electric field produces magnetic field. Complete symmetry. You see what is actually behind this displacement current and the fact that the displacement current produces magnetic field. It's the fact that changing in time electric field produces magnetic field. Okay, on the next slide, of course, I will emphasize on that one more time. But actually, that's the nature, right, of this displacement current. Okay, so now these are properties. So, and now let's actually apply this modified Amperes law, Maxwell's law, for that capacitor system in order to see that it will work now. You remember that example where it failed to work? And now let's see if we fixed the law, right? Okay, so you're, yeah, here. So I just copied and pasted exactly the same picture and reduced just the size, which we had like a couple of slides ago, right, when we discussed and saw the problem. All right, so surface S1, flat one, and this baggy type surface S2, which goes between the plates. Okay, so let's apply modified Amperes law for the flat surface S1. Yeah, simple surface, right? So this is our modified law, right? And so let's look carefully at the currents. So what is I enclosed? Actually, this I in, it's the actual current, which is a drift of electrons. So actual current through the surface S1, it's this current. So this current I crosses the surface S1. So that I in is our current I. Then, what is displacement current? What's the value of the displacement current through the surface S1? We just discussed it. Okay, it's item 1, this. So the displacement current is not zero, only between the plates. If you go outside of the plates, displacement current is zero because electric field there is zero. And our surface S1 is over here, outside of the capacitor. So where displacement current is zero. So over here I can add in my explanation box that I displacement equals to zero. So as a result, the right hand side will be equal to just mu naught times I. So that's what we're getting from using surface S1. Now let's use surface S2, this baggy type surface, concave surface. All right, exactly the same law, you see. And now again, we need to analyze what about I in, actual current, and I displacement. So what can you say about the actual current? Actual current doesn't cross our surface S2. Actual current goes through this gap, right? And ends on the positive electrode. So actual current doesn't cross our surface S2. So I in is zero. But what about displacement current? Yeah, displacement current is between the plates. So this displacement current does actually crosses this surface S2 because this surface S2 goes through the gap between the plates. And we know that numerically this displacement current equals to the actual current. Numerically, we just emphasized it on over here in the item 2, right? So numerically, it is equal to the actual current I. So as a result, we're getting exactly the same answer for both surfaces. Surface S1 equals to mu naught times I, and for the surface S2, it is also equal to mu naught times I. It works now. So Maxwell found the problem and he fixed it, and that's why his name was added to the name of this law. Of course, it's actually not a true derivation. He looked at a special situation, special case in a case of a capacitor, and using this situation, he came up with this term. And now this law can be used anywhere you want, right? And it works. So now no one has ever found any examples where this law would fail to work. Right. Okay, yeah, it's not a true derivation, sort of like a fudging, but once you get the correct result, right, after that, since you are the winner, you can come up with any story, right, at the ceremony of when Nobel Prize, for example, is awarded to you, right? So you can come up with any story that maybe, you're praying and light descended into your head and you saw the term, right? Since you are the winner, of course, you will get standing applause anyway, right? But first, of course, you need to be a winner. Okay, anyway, so he managed to fix it. Great. And so now we have this final form of the Amperes Maxwell law, right? And you remember in the previous class, I emphasized on the structure of all these Maxwell's equations. They all have similar structure. On the right-hand side, we have sources which produce fields shown on the left-hand side. You remember? And now let's look, and here we have the same structure. Okay, left-hand side, magnetic field, which is produced by what? Okay, it's a field which is produced by actual current I in. Again, actual current, it's a drift of charges. And also magnetic field can be produced by what? this displacement current, which is actually just a changing in time electric field. And you see that's why this guy appeared again jumping, right? So here, because changing in time electric field produces magnetic field. I already mentioned a few minutes ago about this, right? So in the Faraday's law, we had which situation? That changing in time magnetic field produced electric field, and this green creature was jumping also, right? Celebrating, because it's a huge conclusion, very important conclusion. And now we're getting a reverse situation, that the reverse situation is correct. Now changing in time electric field produces magnetic field. You see complete symmetry. And that's why I told you in the previous class that these two worlds, world of electricity and world of magnetism, they're basically inseparable. They're so overconnected that it's impossible to separate them. If fields can produce each other. That's why usually this course is called electromagnetism, right? And you see the structure, as I said, the same. Sources and a field which is produced by those sources. And again, the same picture, sort of eternal dance of the electric and magnetic field, because they're basically inseparable. Right? Okay, so that's what I wanted to discuss about Amperes law. So now we fixed it. And now it's correct, and this is the equation number 3 in the set of Maxwell's equations. But we still have one equation which is missing. So let me add that last equation, and then after the break we will start talking about traveling waves. So the last equation. Yeah, before that. Okay. So according to, I just want to again show that similarity, that changing in time electric field produces magnetic field, changing in time magnetic field produces electric field. So in the previous class we saw, if you have a solenoid, right, inside of that there is a magnetic field, and if current through the solenoid is changing in time, then of course magnetic field inside the solenoid also changing in time. So changing in time magnetic field inside of the solenoid is going to produce us induced electric field, right? So electric field is produced by the magnetic field. That's what we saw in the previous class when we discussed Faraday's law. And today we introduce the reverse situation. So if you have now a capacitor which is being charged, and of course electric field as a result changing in time, because charge is increasing, electric field between the plates also increasing. Changing in time electric field, it's our displacement current, right? Changing in time electric field produces magnetic field, which is induced magnetic field. So between the plates of the capacitor, there will be induced magnetic field, right? So I just wanted again to demonstrate the similarity between electric and magnetic world again. So this field produced that field, and now reverse is correct. Magnetic field is produces, and the electric field is produces magnetic field. Right. Okay, and now the last equation, the equation number 4. And we're going to introduce it using similarity. As you already noticed, there are lots of similarities between the electric world and the magnetic world, except one. And that's why, except one. Okay, I will remind you about that in a second. I don't want to jump ahead of myself. Right? I almost jumped. Okay, so you remember Gauss's law for the electric world, for the electricity. It's our first fundamental law, right? You remember it's a integral over a closed surface, E dot dA, it's basically flux, electric flux, through the Gaussian surface, equals to Q enclosed over epsilon naught, right? And you see, we have this law for the world of electricity, but we don't have a similar law for the world of magnetism. Similar means that integral over some closed surface, right? We have two laws, one law for the electric world and one law for the magnetic world with the integration over a closed loop. But we don't have anything for the world of magnetism where we'll have to integrate over a closed surface. So Gut's feeling, there must be a similar sort of like a Gauss's law for the magnetic world, for the magnetic field, right? So let's think how it should, what should be the structure of this law. Of course, it should have something like this: integral over a closed surface B dot dA, right? Again, based on similarity. But what should we have on the right-hand side of this equation? Over here, again, for the electric world, we have Q enclosed over epsilon naught. What should we have here on the right-hand side? At this point, you should be able to guess, right? If you're still not getting this, let me ask you this. On the left, on the right-hand side of this Gauss's law, we have Q charges, just point charges. How else can we call point charges? For example, positive point charge, negative point charge. How else can we call them in sort of like using fancy name, really fancy names? Point charges, for example, positive point charge, it's a positive electric monopole, right? Negative point charge, it's a negative electric monopole, right? So basically here on the right-hand side of the equation, we have electric monopoles, net electric monopoles within the Gaussian surface. But what can you tell about the magnetic monopoles? You remember we discussed that a couple of weeks ago. So far, no one has ever observed magnetic monopoles. And as a result, all our equations are written remembering that fact. So if there are no magnetic monopoles, it means that on the right-hand side of this equation, we should have what? 0. This integral equals to 0. That is the last equation in the set of Maxwell's equations. Basically, this equation just tells us that there are no magnetic monopoles. If you in the future manages to find some magnetic monopole somewhere in the universe, right? This equation will be changed immediately. Once that your discovery will be confirmed, right? This equation will be changed immediately. Right. But for now, since no one has observed any magnetic monopoles, this integral equals to 0. Right. Okay, so finally, all the equations are here, and now let me summarize. So now we're reaching the top of the course, right? Yeah, are we there yet? We've been climbing a lot, right, in order to reach this point, right? And of course, that's why I put this photograph of probably the most beautiful mountain in the world, Amadablam. It's right next to Everest in the same Khumbu Valley. Okay, so equations. First one, Gauss's law for the electric world. Integral over the closed surface, E dot dA equals Q enclosed over epsilon naught. How should you read it? Physical interpretation. You remember I explained to you about the structure. On the right-hand side, we have sources. On the left-hand side, we have fields produced by those sources. So here we can say that electric field is produced by charges. Physical interpretation, an electric field is produced by, okay, a charge, but charges, right? That's physical interpretation. Then Gauss's law for the magnetic world. Integral over the closed surface B dot dA equals 0. The interpretation that magnetic monopoles do not exist. Right. Then the last, the next one, Faraday's law. Integral of, okay, so guys, the first two equations you see, integration over a closed surface. Now the next two equations, integrations over a closed loop. So now we have integral over the closed loop E dot dl equals to rate of change of the magnetic flux. Interpretation that electric field, induced electric field, is produced by changing in time magnetic field. It's a previous class, right? Faraday's law in electric field is produced by changing magnetic field. And the last equation, now modified Amperes law, Ampere Maxwell's equations, which we just introduced. Again, you see integration over a closed loop. Again, two integrals over surfaces and two integrals over closed loops. All right, one for the electric field, one for the magnetic field, electric field, magnetic field, right? Okay, let me hold you for extra a minute in order to complete this. And so now magnetic field is produced. Sources are over here. The actual currents, drift of charges. Magnetic field can be produced by actual currents, and magnetic field is produced by changing in time electric field. The last equation. So that's what we call a set of Maxwell's equations written in the integral form. All right. But is it a complete foundation? Or something else must be added? Look at these equations. All of these equations explain how we can produce fields. Electric field and magnetic field, nothing else. We can produce electric field by this, magnetic field by that. So pretty much all possible ways of producing electric field. But what is missing in order to have a complete set of equations? Now we know how we can produce fields, but how do they interact with the world? We need to add an equation which would describe interactions of all these fields with the outside world. What do we have to introduce? We need to introduce forces, electric force and magnetic force, and add, we did introduce in the past, right? We just need to add that equation to this set of equations. You remember? Electric force and magnetic force. And we're going to combine them and present it as one equation. And usually it's called Lorentz force. So you see, F equals QE, electric force, and then QV cross B, magnetic force. Right? You see, they usually combine and added as one equation to this set of equations. So these 5 equations form the foundation of electromagnetism. So pretty much it's a true foundation. So far, no one has ever found any examples, any phenomena where these equations would fail to work. It means that you can, using this equation, you should be able to describe any electromagnetic phenomena in the universe. So far, no one has ever found example where they would fail to explain. 4 equations describing how we can find fields, electric and magnetic field, and then how those fields interact with the material, with the world. All right. And the rest of the equations, the rest of the laws, right? So those Ohm's law and so on, right? So they all can be derived from these equations. This is the foundation, true foundation, right? And that's why I put this proud, happy peanut picture. Okay, so yeah, Lorentz force. All right, and so now overall in classical physics, there are 11 fundamental equations. Let me just state them, and then we'll we'll have a break. So in the classical mechanics, right, physics 1, you introduce these 4 fundamental equations: Newton's first law, second law, third law, and Newton's law of gravity. Everything is about Newton, right? So he was boringly productive, right? His name is almost everywhere. Then it's a physics 1. Now in physics 2, we introduced 5 additional fundamental equations, which we just stated, right? So Gauss's law for magnetism, Faraday's law, Amperes law, Lorentz force. Additional 5 equations. So overall we have 9. It's a physics 2. And some of you already took physics 3. Some of you will take it maybe next semester and so on. So in physics 3, which is basically thermodynamics, there are 2 additional fundamental equations. First law of thermodynamics and the second law of thermodynamics. It's the least productive part of physics, right? Physics 3, right? So only 2 fundamental laws are added. So these 11 equations form the foundation of the whole classical physics. Quantum mechanical world is not here. Quantum mechanical world is different world, and it has different different way of describing that.